Hello guys, welcome back. Today will be our last lecture video of the series, and we will be doing an introduction to deep learning. So today we are going to create a fully connected neural network architecture. We're going to use this architecture to solve a common regression problem. We're going to train our neural network with stochastic gradient descent, and we're going to attempt to improve performance of our neural network with specialized techniques like dropout and batch normalization. So, what exactly is deep learning? Let's start with the very basic question. So, if you've seen some of the more recent advances in artificial intelligence, AlphaFold, the model that DeepMind created to predict how proteins fold, or AlphaGo, the model that, or the AI that could beat the world champion in the game of Go. Both of these are deep learning models. And these are really revolutionary in the sense that they have exceeded human level performance in these very complex domains. So, how exactly does deep learning do this? Well, deep learning is essentially an approach to machine learning characterized by deep stacks of computation. And this depth of computation is what allows deep learning models to disentangle these complex patterns found in some of these complex data sets. So neural networks are the defining model of deep learning. Neural networks are composed of neurons which perform a single computation by themselves. They're usually pretty simple computations by themselves, but where the power of the neural network comes in is the complexity of the connections that various neurons can form. I mean, in a neural network, in a simple neural network, like we're going to go over today, we're going to have over 1,500 neurons, and it's not going to be these neurons that are doing the themselves solving the problem, but it's going to be the ensemble of these neurons and the connections between them, entangling these complex relationships between the data. So, starting very simple, we have the fundamental component of a neural network, which is the individual neuron. So, diagrammed, a neuron might look like this. By the way, we call this fundamental component a linear unit. You might hear something about a linear unit. It's essentially a neuron. So in this specific neuron, the input is x, and it has a connection to the neuron diagrammed by this arrow, w, which is actually its weight. So whenever a value flows through this connection, you multiply this value by the weight. So what actually reaches this neuron is w times x. A neural network actually learns by modifying these weights, and we'll go over the details of how it modifies these weights and how it learns to modify these weights later on. So this B is what we call the bias. Notice it doesn't have any input data associated with it, it's just a 1. So what will actually reach this neuron is simply B. And we do this because the bias allows the neuron to modify the output independently of the inputs given in. So the output of this neuron is effectively this linear combination here, Wx plus B. And obviously, as we said, these simple neurons do simple computations. These single neurons do simple computations rather. So it's obvious that we're not going to find any crazy relationships. We're not going to solve the game of Go with Wx plus B. So it's these connections. We're going to keep reiterating this idea, these connections that allow us to form these complex relationships. So in code, we simply do use Keras sequential here, and what it does essentially creates a neural network, and it treats it as a stack of layers. So here we simply define our model with Keras.sequential, and we pass in this dense layer. This is a single dense layer. So maybe it'll be better when I explain it in a second. But so let's run this slide. We actually don't get an output. We're just designing the architecture for now. So you might be able to predict by this list here, the fact that we're passing a list, that we might pass in multiple arguments here eventually, and that's exactly what we're going to do. Neural networks typically organize their neurons into layers. So when we collect linear units together, which have a common set of inputs, we get a dense layer. So you could think of each layer in a neural network as performing some simple computation. And reiterating this idea again, it's through this deep stack of layers that we transform its inputs more and more complex ways, so that we're getting closer to the solution as we pass through each dense layer. But if we just keep it how it stands, we actually aren't doing anything. We're not getting closer and closer in between layers. We have no nonlinearity. These are just linear functions, right? So we have to introduce nonlinearity to be able to solve more complex problems. So we introduce something called the activation function. So what an activation function essentially does is introduce this nonlinearity that we need. So an activation function is simply a function that we apply to each of the layer's outputs, and we might use a function that you might have already heard of called the rectifier function. This is a common activation function. The rectifier function simply rectifies its negative inputs to 0. So it essentially takes the maximum of 0 and current input. So as you can tell, any input that's negative will be rectified to 0. So if we apply an activation function to a single linear unit, we might call this a rectified linear unit. ReLU, however you might want to pronounce it. I like ReLU. But we see now that what reaches this neuron is not this simple addition sign that we had earlier, but it's actually this. So it's not y equals wx plus b that's getting output from this neuron. It's actually this. It's the rectifier function 0 or wx plus b. So in doing this in code, we might actually put this after our dense layer, or we can actually put it in one line here and just pass it through the activation parameter of this dense layer here and pass it as a simple string here. There are other activation functions that we might want to use, even ones that are very similar to ReLU, like ELU, CLU, swish. Some other activation functions include sigmoid and tangent. You can learn about those, you can look those up and do some more research on your own as to exactly what those are. But today we're going to be using the ReLU activation function for our lecture's purposes. So now that we have this nonlinearity that we were talking about, we can stack these layers and we can get this convergence to our solution that we wanted through passing each hidden layer. Oh, we introduced a new term there. Well, what is a hidden layer? We simply call dense layers before the output layer a hidden layer because we don't actually see their outputs directly. We don't see the output of this layer directly. The outputs are passed into another layer, which is passed into the output layer, which then we see the output to. So we call these hidden layers because they're sort of like black boxes. Notice in this diagram here, the output layer does not have an activation function. And this is very common when we're trying to use neural networks to solve regression problems. If we were to, go back to the Titanic data set that we did earlier on, we might want to put an activation function at the output layer. But for our purposes, we're doing regression, so we're going to keep it without an activation function at the output layer. So we're using this same sequential argument, and now we're going to actually do a reasonable architecture with an activation function. And we're going to pass it in like so. So this has 4 neurons in this layer, an activation function attached to it, the real U activation function, and an input shape of 2. And then this layer has 3 neurons with the same activation function, and then our output layer obviously has 1 neuron, no activation function. So let's run this code. Let's run this, and now this list makes sense because we're actually passing these as elements of a list, rather than at the beginning when we saw this like these brackets and just one argument. It's kind of confusing. It's like, why do we pass this as a list if it's just one argument? But now we understand we're actually treating this as a list of layers. That's how we're kind of building this model. So now we've designed a simple architecture, but we're still missing a lot. So for one, we're still missing on how to tell the network what problem to solve. So our loss function actually does this. You might have heard loss function, you might have heard cost function. They're effectively the same thing. And essentially what a loss function does is measures the disparity between the target's true value and what the model predicts. So if we're trying to, for instance, predict the ratings of red wine, for instance, and our model predicts a specific instance is has a quality of 9, but the actual quality is 6, we're actually essentially taking the difference between these in our loss functions. So in our case, we're going to be using the mean absolute error loss function. And for each prediction, some people might refer to it as a prediction as an instance, we actually simply measure the disparity from the true value by the absolute difference. So we just do the true value minus the predicted value and the absolute. So in our case, 9 and 6 example, so it would be 6 minus 9, which is negative 3, and take the absolute of that. So our loss would be 3 in that. If we sum up the MAE loss, or sorry, not if we sum them up, if we take the average of all these differences, that's actually just the total MAE loss on a data set. So MAE, I'm going to refer to as MAE for the rest of the lecture. Mean absolute error is what I'm referring to. Okay, well, so we've done this. We've actually told the network what problem to solve. We've given it a loss function, defines how good it's doing at each prediction. So now we're still missing something. Well, we still haven't achieved this, what we were talking about earlier, how a neural network learns by modifying the weights. Well, how do we modify the weights? How do we learn by modifying the weights? We actually can do this. We can tell the neural network how to solve a problem using an optimizer. So the optimizer does exactly that. It adjusts the weights to minimize the loss. So almost all optimization algorithms belong to a family of stochastic gradient descent. So in one iteration of training with stochastic gradient descent, we might follow some process like so. So first, sample some training data and run it through the network, make predictions. Measure the loss between the predictions and the true values, and then adjust the weights in a direction that makes this loss smaller. And essentially, this is one instance, and we want to do this over and over until we converge to a value that we like. So each iteration's sample of the training data, so at each iteration we sample the training data, we call this a batch. And what we call an entire round of training data is an epoch. So the number of epochs that we train for is how many times the network will see each training example. So if we look at this diagram, you might recognize this. This is actually showing the linear model from lesson 1 being trained with stochastic gradient descent. So the pale red dots here depict the entire training data set, while the solid red dots are the mini batches. So at each step, like we said, we sample some training data. At each step, it's sampling some training data. These are the dark red dots. each time our optimizer sees a new mini batch, it shifts the weights towards their correct values. So essentially, this line is converging to its line of best fit using this optimizer. The other, you can see the loss as a function of the batches seen. The loss is kind of oscillating, but the oscillations are getting smaller. It's converging to a value that is better that we might like. So, and then you can see the weights being adjusted here in this diagram as a function of the batches being seen. So you might notice that this line is moving very slowly, very small iterations. So we actually can change that. We can actually change the direction or the extent to which this line shifts at each batch. So we can do that by modifying the learning rate. So a small learning rate means we need to see more mini batches before it converges to their best values, which means smaller shifts in the direction that is desirable. So and obviously the batch size is going to have a big effect. So obviously, suppose that we had a smaller batch size, we're going to sample less training data, and this might pose a problem, for instance. So luckily, today we won't try and tune these parameters too closely. But knowing the definition, knowing what these do, is pretty important. So actually, in order to kind of avoid this guess and check, this tuning these hyperparameters, we're going to use an optimizer that is somewhat self-tuning. So essentially what it does is adapts its learning rate that makes it suitable for most problems without this tuning. So it's self-tuning essentially. This optimizer is called the Atom Optimizer, and it's a great general purpose optimizer, and we're going to use it for that exact reason. We're not going to introduce too much of the difficulties, the intricacies of neural networks and tuning parameters and such today. So to actually add the loss in the optimizer, we simply use the model's compile method and just pass in these two arguments via, as strings essentially. This is pretty convenient. So now let's get into actually applying this architecture to solve a real world problem. So we're going to be using the red wine quality data set, which consists of physiochemical measurements from about 1,600 red wines. So included is a rating for each of these wines. So let's use what we know about data visualization to visualize some of the data here. So we have these physiochemical measurements here. Volatile acidity, citric acid, residual sugar, such like that. We luckily, as data scientists, we don't really know how to characterize these. All we need to know is how to create these models and how the data is structured. So luckily, we don't have to know exactly what all these mean exactly, but so essentially what we're trying to predict is the quality of each instance. So we're trying to predict this value. And something to note when you're designing an architecture, the input shape of your neural network is always going to be the same as the number of columns in your data frame. So let's run shape on the trained data set. We're going to see that it has 9 columns. So the input shape to our neural network is actually going to be 11. So now let's create a network that might be able to do some regression, hopefully pretty well. Hopefully it should learn relationships in this data. We're not totally sure how complex this data set is yet, but for now we're going to do minimal pre-processing, and it shouldn't be too difficult. It's a very common, readable, balanced data set. So let's run this. We have a lot of neurons, by the way, not 3 and 4 like we said earlier. We have 500 neurons in each layer and only 3 layers, and so that totals up to more than 1,500 neurons. So regression problem, like we said, so no activation function, this last argument here. And then here we compile using the optimizer and loss function, run this, and now we can train our neural network, and we can actually see how it does. Um, so today, or for this example, we're going to feed the optimizer 256 rows of the training data at a time. So how many rows of the training data are there? There are a lot, and we're going to be feeding about a fifth of this. So yeah, and we're going to do that 10 times because there are 10 epochs. We might be able to, so let's run this with 10 epochs for now and see how it does. Luckily, we see our loss value getting smaller and smaller and smaller and converging to this value here. Is it always best to just, like, what if we just ran as many epochs as we possibly could? Would the loss just keep getting smaller? That's not actually the case. Let's run 50 epochs, for instance, in, oh, not 150. Let's run 50. So we don't want to be here all day. So it's getting smaller still. We might have to run we might have to run a lot more to be able to see this relationship that I'm trying to get at. So essentially, sometimes we might we're going to reach a value of convergence where our neural network can't do any better. So it's sort of important to know and to be able to tune the epochs parameter such that we don't run too many epochs. We run as little epochs as we can to get the best loss value. Because we don't want to just run as many epochs as we can, because that takes a lot of time. We want, if big data sets, neural networks take a long time to run, we don't want to run that many epochs. We want to hopefully not fall to this diminishing marginal returns that we might see running with more and more epochs. We might converge to a value, say at epoch 10. And in that case, why would we run 50 more epochs if we're already at a suitable loss value? So just a little rant there. Now let's visualize how the loss changed over time. That's because of our 50 epochs. I just realized it's not supposed to look like that. Let's kind of redefine this, rerun this, and so this is kind of what I was going for here. This nice little this curve here that we see the loss getting constantly smaller and converging to this value here. Obviously we can get a little smaller, but we saw that sort of little oscillatory behavior in this last plot, and we don't want that sort of behavior, even if it means going for a little bit of a lower loss value. So now we can get into, I think, what's a little more fun about neural networks. We don't just add a bunch of dense layers to a neural network. There's actually much more than just dense layers. We can add specialized layers that do very interesting things and transform our data. So some can do pre-processing and transformations of other sorts. So today, we're only going to go over two kinds of these special layers, but you might be able to look through Keras docs for some cool special layers, some interesting ones. But these two are, in my opinion, some of the more useful ones for uncovering complex data sets and giving you an introduction to these specialized layers. First, this is the dropout layer. The dropout layer essentially is used to combat overfitting. You might recall, overfitting tends to happen when a model, in our case a network, learns very specific patterns to training data. So it recognizes patterns that are there in the training data, but really only there in the training data. They're not there in all wine data sets, for instance. They're in there in this in our training data only. So then when we give it some new data set, or some new instance of the wine data set, for instance, the accuracy is going to greatly decrease. So essentially our models overlearn. They overanalyze. So we want to avoid overfitting. So essentially we can add a dropout layer. So essentially what a dropout layer does is drops out some fraction of the layer's inputs at every step of training. In this case, we have a dropout layer added between the two hidden layers, which drops 50% of the input layer in this step of training. So this essentially decreases the probability that our neural network is going to learn very spurious patterns and overfit to the data set. And we can add this pretty simply by adding it in between dense layers. As you see, basically, we can kind of visualize it like between these two layers here, if you will. Okay, so and we pass this rate argument, which is here we specify 50%, but when we add this, so in this case it'd be rate equals 0.5 between these two hidden layers here. Another special layer we're going to look at is batch normalization, which you might know by the name. We're going to be doing some sort of a normalization to the data. So essentially, we're going to be able to, with the batch normalization layer, we're going to correct training that is slow or unstable. Well, why might training be unstable? Well, suppose that we have data which has features that tend that have activations of very different sizes. Well, if we think about how stochastic gradient descent works, it will shift the network weights in proportion to how large an activation the data produces. So if we have these activations of very different sizes, and it's going to shift the network weights in proportion to the size of these activations, then we're going to get unstable training behavior by default here. So normalizing the data seems like a good idea. So, but it might make sense to normalize the data before we put it into a neural network. But stochastic gradient descent happens inside the neural network. So luckily we can fix this sort of dilemma with a batch normalization layer, where we essentially normalize the data inside of the network. So this layer at each batch normalizes the batch and then puts the data on a new scale with trainable rescaling parameters and normalizes it at each step. This is seemingly magical in my eyes, so it's pretty cool. So and essentially we can add this as an aid to the optimization process, and it will likely help prediction performance in some cases, but sometimes we can fix this sort of. So imagine we have a neural network and we train it for 50 epochs, and it kind of gets stuck at a value, but we know that it can get better. So it gets stuck at 0.5 loss or something. We know it can better. Batch normalization can actually sort of fix the problems that might cause training to get stuck at this high loss value. So this is a very good thing to add to your neural network, to your models, especially if you're seeing sort of this behavior of unstable, slow, this early convergence of your training. So we can do this in two ways. Let's suppose we put it after a layer here in its own argument here. We have this dense layer activation, and then we have this batch normalization. Or we could do it like so, where we put it in between the dense layer and its activation function. Either way, it's actually equivalent, so it doesn't really matter. It's a matter of preference. Most people, I think, like to do it this way, just because people like adding their activation functions in the same in this one argument, the dense layer. All right. So now let's perform regression on the wine quality data set again. But now we can actually add dropout to control overfitting, batch normalization to speed up the optimization. So we really, it didn't seem like we saw the problems of unstable or slow training behavior. It's a very simple data set. So batch normalization might not do much, and additionally, dropout, it didn't seem like we were overfitting, but we might have been. We'll see if we can get better loss values for this using these new special layers. Let's just run these, and none of this has changed. All this is the same in terms of the optimizer, the loss, training data. We added more epochs here. If we could run it for 10 if you'd like. and then run it for 100. So our loss value actually is a little a little higher than what we had without the batch normalization and dropout layers. So let's try and add more epochs, for instance. Let's add 100 epochs. So let's see if we get better performance with more epochs. I don't know why I'm scrolling down like that. We'll get it after. All right, seems to be done. So our lowest loss value, it's in the 0.1s, right? That's actually a little higher than what our model was predicting without these batch normalization dropout layers. So we'll also notice that our layers are actually bigger. So we could, if we want. I see. So let's modify this real quick so this is the same exact neural network except for with these layers added in. Let's see what happens. Let's see. Okay. So doesn't seem like there's any change actually. But I just wanted to use that as a direct form of comparison so that you might not be fooled into thinking that the reason we had this issue is these is adding more neurons into each layer. So same thing, getting a little higher than we would like. We're still seeing this behavior, like good behavior, good data, good trends of the loss value. But we didn't get better performance with these, but that really is just speaking to how good this data set is and how we weren't really facing these problems of overfitting or unstable training behavior before, so we didn't really need to see it. But yes, so this concludes this lecture video and also all lecture videos in this course. I hope you guys enjoyed this course. I hope you guys enjoyed the assignments. I hope you guys enjoyed all of it. I hope you guys learned a lot. And I was very happy to give you guys this lecture. I'm very passionate about this subject, and I hope that you guys take away something from this lecture, and I hope that you guys hopefully formed a passion of yourselves, because deep learning is a very intriguing field, very interesting. Machine learning as a whole, data science as a whole, very intriguing field, and I hope that you guys took a lot from this class, and I hope that you guys feel comfortable in going out and solving complicated problems that you guys are passionate about. So with that, I will bid you guys adieu. I appreciate your guys' company, and I hope you guys enjoyed the assignments on deep learning. And I hope you guys have a good rest of your day, night, whatever time it is when you're watching this. But I hope you guys are well, and good luck.